Next we have example 2. A laser pointer is placed on a platform that rotates at a rate of 20 revolutions per minute. The beam hits a wall 8 meters away, producing a dot of light that moves horizontally along the wall. Let theta be the angle between the beam and the line through the searchlight perpendicular to the wall, as in the figure below. How fast is this dot moving when theta equals pi over 6? So here's the situation. We've got a right triangle here. And we know we are given the rate of this theta, so how this theta is increasing. So again, just like the previous example, a very common geometric setup here is a triangle for these related rate problems. But just because you have a triangle involved in the problem doesn't automatically mean you're going to use Pythagorean theorem. In this case, we're not going to use Pythagorean. The reason for this is our given rate of 20 revolutions per minute is an angular velocity. It's a rate of change of an angle. Pythagorean theorem allows us to relate the three side lengths of a right triangle, but it does not have any connection to the angle. So we're going to have to somehow find something else. So let's go ahead here and write some things down. Ultimately, we want to know how fast this distance is changing. So let's give this distance a name. Let's go ahead and say that this distance is x. This is a right triangle. So if we want to somehow relate x to theta, and we also know that this side length is constant of 8 meters, then we can use a relationship from trigonometry. We can go ahead and say that the tangent of theta is equal to the opposite of theta, which is x over the adjacent 8. This is our relationship. So now, let's just move that to the side and say our goal is to find the rate of change of x with respect to time when the angle theta is pi over 6. We are given our rate of change of theta is 20 revolutions a minute. But we have to be careful here. We have to be very careful here. It's very tempting to say this is equal to 20 revolutions per minute. But the units on this side are not equal to the units on this side. Why is that? So let's backtrack for a second here. So we measure theta in radians. So this should have units of radians per some unit of time, whatever we're measuring time in. In this case, it would be minutes. But it doesn't have to specifically be minutes. It can be some unit of time, whatever the units of t are. So for us, it's going to be minutes. So radians per minute. But what we're given here is revolutions. So in this case, 20 revolutions per minute, per 1 minute. Well, a revolution is not the same thing as a radian. There's a discrepancy. So, in 1 revolution, how many radians are there? 2 pi radians all the way around. So, then these units cancel, and we're actually left with 40 pi radians a minute. And that is actually our given rate. So you got to be careful. Okay, now that we have that taken care of, converted revolutions into radians, now we can take our rate. and differentiate. So we'll take the derivative with respect to time on each side. Derivative of tangent is secant squared. So get secant squared theta d theta dt equals 1/8 dx dt. And we're interested in solving for dx dt, so we have dx dt equals 8 secant squared theta d theta dt. With that, we are free to go ahead and plug in what we know. So let's do this over here. Dx dt, when theta is pi over 6, is equal to 8 times the secant squared of pi over 6 times our 40 pi. And this would be, in this case, meters per minute. So this should be 8 times secant of pi over 6 is 2 over root 3. So 2 over root 3 squared times 40 pi. If you simplify all of this, get a common denominator, or not a common denominator, but you reduce the fraction as much as possible. This turns out to be 1280 pi over 3 meters per minute. All right.